Hello everyone, I'm Mohan Bhupal and I'll be continuing the lectures of Math 219. In this lecture, I will give an introduction to systems of first order equations and a review of matrices. So we'll start with the definitions, so systems of first order linear equations. Sorry, not linear, just first order equations. We'll come to linear after we discuss the general case. So a set of equations of the form x1 prime is equal to f1 x1 x2 to xn and t. X2 prime is in a similar way f2 x1 x2 to xn t and so on up to xn prime is equal to fn x1 x2 xn t. Okay, a set of equations of this form is called a system of first order equations. Order ODEs. So here, x1, rather, these f1 up to fn, these are just arbitrary functions. So here, f1, f2 up to fn are functions. x1, x2 up to xn and t. So that's a system of first order ODEs. So let me give you a quick example. So let's take the system of equations. So when we have, typically if we have 2 or 3 variables, we will call these, instead of x1, x2, we may call them x, y, z, and so on. So yeah, this will be a system with 2 variables, 2 dependent variables. So we have x1 prime. So x prime is x minus, say, a half xy, and y prime is, say, minus 3/4 y plus 1/4 xy. So here's a system of 2 equations in so we have 2 equations and 2 unknowns here, so we can think of. Sorry, this is a system of 2 differential equations, and we have 2 dependent variables, x and y. Notice that t does not appear on the right-hand side. So this, for example, this equation, this system of equations, this could be a predator-prey model, for example. Predator-prey model. So for example, X might denote e.g. xt, this might be the population of rabbits. And yt equals a population of, say, fox. So this is a predator-prey model. The predator is fox and the prey are rabbits. And the first equation, x prime is equal to x minus half xy. This denotes the rate of change of the population of rabbits. So here, there's a positive coefficient of x in the first equation. So the more rabbits there are, the faster they'll breed. So that sort of makes sense. And the second term, xy term, we can think of this as interactions between the predator and prey. So as the number of interactions increases, this might cause we might expect that the rate to decrease according to that. So that is a reasonable equation for the prey species. So for the predator species, we have y prime is equal to minus 3/4y plus a quarter xy. So the negative coefficient of the y, we could think of that as overcrowding. So if there are more fox present, there might be less space, less resources, etc. So that might cause the rate at which the fox were increasing to decrease. And the positive coefficient of the xy term, so that's interactions. If there are more interactions, then we might expect that to have a positive effect on the rate of increase. So that's just an example of a system of equations. Okay, so next we come to a solution. So a solution, so let me, before going to that, we'll be referring back to this set of equations. So let's call this set of equations 1. Okay, so we'll discuss a solution of an equation such as 1, of the set of equations such as 1. So a solution of a system of first order ODEs this is an n-tuple of functions x1 up to xn of t. That satisfy the equations, so in our case 1, on some interval I say. Okay, so as we've considered for first order equations, typically we expect to get infinitely many solutions of a system of differential equations. And so here, if you're looking for just one, we will initial conditions are something that we typically impose. So here, an initial condition so this is a specification of the n values x1, t0, x2, sorry, this is, say it's equal to something, say a1, let's call it x2 t0 is equal to a2 up to xn t0 is equal to an. So here, where t0 is some, so t0 is some initial point in time, and a1 to an are some constants. Okay, so let me give you an example of a system of equations with an initial condition. So, example. So consider the initial value problem. X1 prime is equal to x1 plus x2, and x2 prime is equal to 4x1 plus x2. Okay, so this is a system of two equations, two differential equations. So here we call them x1 and x2. So this is also possible. And here our initial condition will be x1 0 is 5, and say x2 0 is 7. Okay, so we don't know how to solve this yet, but let's check that. Let's verify that. X1 t is 4e to the 3t plus e to the minus t, and x2 t equals 8e to the 3t minus 2e to the minus t, that this is a solution of our system of equations and of the initial value. So is a solution of the initial value problem. And in fact, this is for all t. Okay, so how would one check something like this? In fact, one would just substitute x1 and x2 and check that it satisfies those differential equations. So, so let's just do that. So let's take our x1 and x2 and substitute them into our differential equations. So we have x1 prime is equal to 12 e to the 3t minus e to the minus t, and x2 prime is equal to 8, rather. This is 24 e to the 3t plus 2 e to the minus t. Because that's x1 prime and x2 prime. And so let's check what we want. So let's compute x1 plus x2 now. So x1 plus x2. So we have here x1 is equal to 12. x1 plus x2 is 12 e to the 3t minus e to the minus t. And the second equation was 4x1 plus x2. So 4x1 plus x2 is equal to 16, that's 24 e to the 3t. And we have, this is going to be plus 2 e to the minus t. And we can see that, so this one is precisely equal to x1 prime. This is precisely equal to x2 prime. So we can see that x1 and x2 satisfy the equations. So x1 and x2 given as above is a solution of the equation. As given above. Of the system. Okay, so as we had for first order, single first order equations, we had an existence and uniqueness theorem. There's a similar existence and uniqueness theorem for systems of first order equations. Let me state this now. So let's consider the system of equations. One, together with the initial condition x1 t0 is a 1 up to xn t0 is a n. Let's suppose that each of the functions fi x1 up to xn comma t and the partial derivatives of the fi's with respect to xj that these are continuous. Suppose that fi is continuous in a rectangular box or alpha 1 is less than x1 is less than beta 1. So that's the constraint on x1, and we have similar constraint on all the other xi's. So we have alpha n is less than xn is less than beta n, and also that t is constrained. So we have, say, gamma. So we have t between, say, gamma and delta, and we assume that this rectangular box contains our point A1, A2 up to AN and T. So T0. So T0 is our initial time, and A1 up to AN, those came from the initial conditions. So we assume that this is contained inside this rectangular box R. Okay, providing these conditions are met, then there is a unique solution to the initial value problem. So it's an initial value problem. One is the equation and the initial conditions. So let's call these initial conditions. Let me just write, let me give this a number, let's call this 2. So 2 refers to these initial conditions x1, t0 equals a1, up to xn, t0 equals an. On some open interval containing t0. So we can't say how large this open interval will be. It's just going to be some interval which contains t0. Okay, so that's the existence and uniqueness theorem. And when n is equal to 1, you can see that this is just the existence and uniqueness theorem that we had for a single first order equation. Okay, so as we had for first order equations, so these were nonlinear equations. This is a system of first order nonlinear equations. We can also consider first order linear equations. So let's define those now. So I'll give a definition here. So a system of first order equations is said to be, it's called linear. If it can be written so as in the form x1 prime is a11t times x1, and then we have some other terms here, so up to a, let me put the second term in as well here. a12t x2 is all the way up to a1 and t xn plus b1t, and we've got x2 prime is a21. So in a similar way, we have x2 prime. So this is the same sort of equation with 1 replaced by 2, and so on. So xn prime. So there's a typo here. an2 t nnt xn plus bnt. So this is a system of, this system of first order equations is called linear. So any system that can be written in this form is called linear. So here again, so here these were these aijt's and these bit's. So these are functions of t. Okay, so for reference, we'll call this system 3. Okay. If all the bi's happen to be identically 0, so if all of these bit's are identically 0 for all I, the system is called homogeneous. Okay, so in fact, the second example of a system of equations we gave was linear. So if we go back to that, so that was this system of equations here. This is a linear system of equations, and in fact, you can also see that this is homogeneous. So there are no BI terms. So this is, in this equation, we have a system of, this is a system, a linear system of equations, a homogeneous linear system. Okay, so as we might expect, there is a stronger existence in uniqueness theorem for systems of linear equations, and let's state that now. So consider the system of linear equations 3. Together with the initial conditions or just initial condition rather. Initial condition x1 t0 is equal to d1 to x and t0 is equal to dn. So to refer to these initial conditions, let me call them 4. So let's assume that each of these aij's and bit is continuous for t in some open interval say alpha beta, which contains t0, then there is a unique solution of the initial value problem consisting of the system of linear equations 3 and 4, and there is a unique solution of the initial value problem 3, 4, and this is defined on the whole of the interval alpha beta. So just to check, so the previous example we had, we actually gave a solution of it. So that was an initial value problem. And there, everything, so it was actually, the coefficients were constant. So they were continuous for all t, you can think. And the solution we had was given, the solution we obtained was defined on the, let's see, so here we gave this solution, and this was valid for all t. Okay, so that's what the theorem, we expect from the theorem. Okay. So let's note that the system of equations 3 of linear ODEs 3 can be written briefly as I mean, let's say firstly that it can be just written in the following way. So it can be written as x1 prime, xn prime. So using matrix notation in the following way. A11 up to A. So these are all functions of t, so maybe I should specify that here. So times x1 up to xn plus these b1 t up to bnt. And now we can write this more concisely, i.e. x prime. So if we think of x as the vector x1 up to xn is equal to A, so some matrix times x plus b t. Okay, so we'll discuss what this actually means, but here we should think of this. So we've written our system of equations as a single equation. This is a matrix equation. And this looks very much like a linear first order equation. And we're going to use methods of linear algebra to derive a solution of this. So typically we'll be considering the case where A is a constant matrix. Okay, so, but I mean, the theory will also say something about the case where A depends on T. Okay, so that's our aim, is to understand this equation and find solutions of it. Okay, so for this, we'll need to recall some linear algebra. So to understand this equation. And how to solve it. We need some linear algebra. Okay, so we'll start off with a review of matrices. Okay, so you've probably met these before, so we won't give too many details, so we'll be quite brief here. We'll just review the things that we will need directly, and what we won't give proofs. So let's start off with matrices. So the definition, an n by n, or rather, it can be general, I mean, not necessarily square. So an m by n matrix A of real or complex numbers is a rectangular array consisting of real or complex numbers. Okay, so by that we mean that A is some array of numbers. So it's like this. We have A11, A12 to A1n, A21, A22, up to A2n, and up to AN1, AN2 to ANN. Okay, so this is our rectangular array of numbers, and we'll enclose it in large parentheses. Okay, so here this is what a matrix is. A matrix is an array of numbers of this form. So here, so I think I suddenly made this square. Sorry, this should be here. So this is it's better. So we have m rows and n columns. So the rows are so the ith row, for example. So this is equal to a I1, a I2, up to a I n. Okay, so we have m rows, and this is the ith row and the jth column. So this is equal to, if I just write this correctly. So this is A1j, A2j, up to AMJ. So this is the jth column. Okay, and the entry in row I, column J. Column J. This is AIJ. Okay, so for brevity, we sometimes write A is equal to AIJ. Okay, so now let me give you some operations on matrices. So let's discuss some operations that we can apply to matrices. So we can take the transpose, the conjugate, and the adjoint. And so these are defined as follows. So definition, let's let A be a matrix Aij, and for the conjugate and adjoint, those are defined for complex matrices. So let's assume that these are matrices of complex numbers. Okay, so the transpose of A denoted denoted with A capital T, superscript capital T. This is the n by m matrix AJI, and the conjugate of A denoted A bar. So this is the m by n matrix Aij bar. This is the complex conjugate of the entry Aij. And the adjoint of A is the matrix. So we'll denote it A star, and you take the conjugate and the transpose of A to obtain it. Okay, so just a quick example of these notions. So if A is the matrix 3, 2, minus I, 5I, 1 plus I. So I here is the square root of minus 1. Root 2I and 5 plus I. So then A transpose, this is the matrix 3, 1 plus I, 2 minus I, 5I, root 2I, 5 plus I. So we've sort of reflected this matrix in the diagonal A, and we obtain this as A transpose. The conjugate is you take the conjugate of each entry. So real entries, you do nothing, and for complex ones, you replace the, you negate the coefficient of I. So you have 2 plus I minus 5I, 1 minus I, minus 2I, and 5 minus I. And so the conjugate is, you apply both these operations. So if we have A transpose here, and if you take the conjugate of that, so you get 3, 1 minus I, 2 plus I, minus root 2I, minus 5I, 5 minus I. Okay, so those are those notions. So now we'll come to binary operations on matrices. So addition and multiplication, and also the operation of scalar multiplication. Okay, so let's let A and B be n by n matrices. Be n by n matrices. So we define the sum of A plus B just by summing the individual entries. So this is, so the ij entry of A plus B is given in this way. And if C is a real or complex number, or in the complex number field, CA, we obtain this. This is just, you multiply each entry by A. Okay, and let me say we can also define, so we can define the difference as well. This is just equal to A plus minus 1 times B. Okay. So let me give you an example. So let's let A be the matrix. So I won't put any complex numbers, I'll give you simple matrices. So here's two matrices, and their sum is, we just add the corresponding entries. So we get 1 minus 1 is 0, 2 plus 0 is 2, 3 plus 2 is 5, and so on. 8. And if C is equal to, say 2, so we have 2A is equal to, just multiply every entry by 2. 8, 10, 12. Okay, so now multiplication of matrices is slightly more non-trivial. So this is, so if A is an m by n matrix, n matrix, and B let's say this is B is an n by p matrix. Then the product is defined to be the m by p matrix. Cij, where, so this entry Cij, so this is the sum of, say, k is equal to 1 up to n a I k b k j. Okay, so we have this slightly strange way of defining the product. So, and the sizes, it's important that the sizes be appropriate. So when you multiply A times B, so A times B is defined if this is m by n, and this is n by p, and then this is going to be is equal to C, and this matrix C is going to be an m by p matrix. So the n's go and they get summed out, and you get left with an m by p matrix. So if I give you just a quick example, so e.g. So let's go, let me give you a matrix. Let's say A is the matrix, for example. So and say B is the matrix, let's say the one we had the previous, let's just give a simple matrix, one we had before. Okay, so then, so here this is a 2 by 2 matrix, and this is a 2 by 3 matrix. So the product makes sense, and AB is the matrix. So it's going to be minus 2 times 1 plus 4. So this is 2, and then it's going to be minus 4 plus 5, which is 1, and so on. So, yeah. Okay, so this is the product here, and notice that BA is not defined. Okay, and even if it were defined, typically AB is not equal to BA. Okay, so let me state some properties of matrix multiplication. so rather properties of these binary operations that we define from matrices, properties of matrix operations. So let's suppose that A, B, and C are matrices of appropriate sizes, and so we have A plus B is equal to B plus A. So addition of matrices is commutative. If it's defined, it's commutative. So A plus 0 is 0 plus A is equal to A. So here, 0 is the 0 matrix here. 0 denotes the 0 matrix, the matrix of containing all 0 entries. All 0 entries. Okay, so the size must be appropriate for addition to be defined, of course. We have A plus minus A. So minus A, this means minus 1 times A, of course. So this is equal to the 0 matrix. We have associativity of addition. Now, for scalar multiplication, so scalar multiplication, we have so C. When I say scalar, we distinguish. So these are just numbers. So C is a real or complex number. So C, we call it a scalar. We say. So to distinguish it from these matrices or vectors. We have A times BC. Okay, so now assume that A, B, and C are such that this matrix product is defined, so that this will also be defined, and we have equality here. So this is associativity of matrix multiplication. And we have certain distributive rules. A, B plus A, C, and A times, so here again, C, small c is a scalar. This is C, A, B. Okay, so C, here's a scalar. Okay, so these are the properties of matrix operations. So as we said, multiplication is typically not commutative, but apart from that, we have some of the properties that you're familiar with of real numbers. So we can check all of these just directly from the definitions of addition and scalar multiplication and multiplication. So they're all fairly straightforward. Perhaps the only one that's not so straightforward is the associativity, checking if that matrix multiplication is associative. And that actually, one can give an elegant proof of that by noticing that matrices really correspond to special types of functions between spaces like Rn and Rm and so on. And so these are between certain spaces. We call them vector spaces. And so these correspond to functions between vector spaces. And the associativity is, so multiplication corresponds to composition of functions, and composition of functions is associative, so that's why we have this associativity property. Anyway, I won't check the proofs. The proofs, if you haven't seen them before, it's a nice exercise to do. Okay, so, so now we'll talk about invertibility. And determinants. So a definition. So the n by n identity matrix is the matrix with entries 1 if I equals j and 0 otherwise. So it's an n by n matrix. And we call this this is the n by n identity matrix. So we have, for example, 1 is the 1 by 1 identity matrix, 1, 0, 0, 1. It's the 2 by 2 identity matrix and so on. So this is the 3 by 3 identity matrix with 1 along the diagonal. Okay, so those are various identity matrices. So then you can easily check that A times the I. If you take an arbitrary matrix and multiply by the identity matrix on the left or the identity matrix on the right, you get A. So here you have to choose the appropriate identity matrix. So if A is, if this is an n by n matrix, so then this will be the m by m identity matrix, and here this will be this is going to be n by n identity matrix. So we certainly have this, and we're interested in when does a matrix have an inverse. So inverses will only we will only consider inverses of square matrices. I mean, they don't make much sense in otherwise. So so definition: if A is an n by n matrix, we say that an n by n matrix B is an inverse for A if A times B is equal to B times A is the identity. So notice that note that if an inverse of A exists, it must be unique. So why is that? Since if B1 and B2 are both inverses of A, so then we have the following. So B1 is equal to B1 times the identity matrix on the right-hand side. And we have this is equal to B1 times A times B2. So A times B2 is the identity since B2 is an inverse of A. And we from the associativity property, this is B1A times B2. And since B1 is an inverse of A, this is identity times B2. And from multiplication, for the properties of multiplication by the identity matrix, this is just B2. So B1 is equal to B2. So it makes sense. We can say the inverse. So if A has an inverse, we will denote it by A. We will denote it by the symbol A superscript -1. Okay, and the question is, how do we tell if the inverse exists? There's the standard way is by considering determinants. So let me just say a few words about these. And once we've defined determinants, then we'll be able to tell very easily whether a matrix is invertible or not. So determinants, you may have met them for 2 by 2 and 3 by 3 matrices. Let's say how they're defined in general. So let's let A be n by n matrix of real or complex numbers, of real complex entries. We define the determinant of A. We also sometimes denote it just with vertical lines inductively as follows. So if n is equal to 1, we define the determinant of A. Then A has just got a single entry, A, and we define the determinant of A is just with a single entry. And if n is bigger than 1, let's let Aij be the matrix obtained from A by deleting row I and column J. So then we define determinant of A is given by this sum. So it's J equals 1 to n minus 1 to the 1 plus J times A1J determinant of capital A1J. So we call this the cofactor expansion along the first row. And in fact, we can define determinant. It turns out that the determinant can also be given by cofactor expansion along any row. So we can define this for any I. For any I. Okay, so that's the determinant, and you can easily see that if n equals 2, you can see that so then you have A is equal to A, B, C, D, and you can see that this definition reduces to that. So then you get determinant A is equal to, so what do you have? You have here, so delete so it's A times D, so this the minus B times C. If you check what we have here, you get exactly this. and and so on. So if I give you an example of a computation, and you have here, we have determinant A. So this is 2 times determinant of this minus 1 times determinant of, so we delete the first row and the second column, so you get 3, 5, 1 minus 4, and you get plus minus 2 times, delete the first row and last column. And if you multiply this all out, so I'll just tell you what the answer should be. So you get minus 23. Okay, so you can check that. Okay, and here's the theorem. The theorem is that let A be an n by n matrix. Then A inverse exists if and only if this single number, determinant A, is non-zero. Okay, so so at this point I'll stop for today. So see you next time.